I think we're just going to jump right into it, especially because I'll be starting with a review of what we were talking about at the end of last lecture. So welcome, everybody. Today we're going to be talking about synchronization in Rust with regards to multi-threading, and we'll start transitioning into some new interesting synchronization primitives that Ryan's going to continue talking about on Thursday. So first off, I want to reiterate what we were talking about at the end of the last lecture, which was this link explorer thing, so the idea is, you can try to like hop between Wikipedia pages and try to like start at like some word like, I don't know, like dysentery. I don't know why it chose that. It's pretty random. And then like get to revolver, right? But for our purposes, we're going to try something a little bit simpler, and we're just going to see, can we just scour the entire Wikipedia page and try to find the link that has, say, like the largest web page, so to speak, in terms of like the size of the HTML, right? So we're going to try to do this sequentially, and I think I showed y'all last time. I'll actually just swap out of the presentation right now, and I'll share another screen. So I will share my terminal. So can everybody see that? So I'm actually going to split, and then we will, I'll show you, actually let's get out of, so I'll show you the sequential version, Link Explorer. It's very sad. So if we just go cargo run right here, this is how it's doing it sequentially. It's just going through all of them. They're like, there are a lot of links, but you might be wondering, like, you could probably overlap this. So I actually ran this, and I think it ran for something like 3 minutes or something, which is not very exciting. But if we do it multi-threaded, so if I go to Link Explorer Multi, and then if I just do cargo run, it's able to rip through all of them pretty quickly. Still not, I guess, not like blazingly fast, but there are a lot of links. Come on, so this is pretty exciting. And artificial intelligence, as we saw last time, is the most important topic in all of computer science. So I thought everybody should know that. I guess that's what Wikipedia thinks, at least. So let's open up. Let's actually look into this code a little bit. I brushed over it really quickly last time, so I actually want to look into it more. And I'm going to open up main.rs so we can see it right there. Let me see if I can actually make this a little bit wider. Can everybody read that okay? Is that okay? Yeah, I'm going to see if I can drag that to the left there. So there's this library called request with a W. So that's exciting right there. And I do this thing, request block and get, to get the actual, this is kind of like the root page, so to speak. So this is the multi-threading page. And this is just performing an HTTP request. We're going to talk about networking a little bit later, but when I say HTTP request, think of it as I'm downloading the web page. I'm downloading the HTML of that web page. It's just a bunch of text. So I go to a server and I say, server, could I please have the string that represents this web page? And I get that back and I store it in body. And then what I'm doing here is, these are some functional Rust shenanigans basically, but I'm just filtering the body to look for certain tags. So I'm looking for a particular link tag right here. That's all that code there is doing. So while the really exciting part of this, though, is the fact that we have to use a mutex to protect a shared piece of data. So take a look at this right here for a moment. We have a little struct article that's starting at line 18 right there. And you might be wondering, first of all, why do I need to make a struct to store the URL and the len? So I guess based on what we talked about mutexes what we said about mutexes last time, like why do you think I might need to group these two things together in one struct? Can somebody just give a quick answer to that? So what do people think? Or maybe it might be more helpful if we see how the mutex is constructed right here to remind you of how that works. So that's happening on this line right here, on line 45.
Where does it get used?
Where does it get used? It gets used, so longest article, we clone it right here, and it gets used over here when we obtain the lock on it. I guess my question is kind of, in Rust, could I have used one mutex to protect two separate things if they were not already like the same piece of data? And why not? What do people think? Any thoughts? Maybe it might be helpful to think about, this arc, it's wrapping a piece of data, and this mutex, like how is this like what does the constructor of the mutex look like, right? Two references to, do you mean in what sense? Exactly. It's a reference wrapper, right? But why is it that I can't have this one mutex just protect two separate pieces of data? Like if this is what we know about the interface, like if we know that the constructor looks like this. Really, I'm trying to like get to something about the constructor, I'd say.
So to contrast this with C++, in C++, you would just have two variables, and then you would have a third mutex variable. And before you use either of those two variables, you lock the mutex, and then after you're done touching those variables, you lock the mutex again. You don't have to put the variables in a struct or a pair or anything. But Armin is saying that here, it's not like that. We don't have two separate like URL and longest length variables. We put them inside of an article struct. And actually, we had to do that. Why did we have to do that?
Mm. So I'd say it mainly has to do with the constructor of new. Precisely, that's exactly right. The constructor of the mutex needs to take some data to protect. In particular, it needs to take one piece of data. So if I want to protect two things with the same mutex, I need to package them together into the same struct, like an article right here. And I'd say from a design standpoint, this is actually very nice. This is called like the monitor style, I think, of like concurrency, where you want to take pieces of related data and group them together. We're forced to do that by Rust's type system because the mutex, the constructor, takes in exactly one piece of data. Does that make sense to everybody? Are there any questions about that? I think it's totally fine if there are questions, because when I first saw this, I was very confused. Like the mutexes I've seen before, they don't take anything in. It's just like, you declare a mutex and then you lock it and then you unlock it, right? The weird thing here is that when we lock a mutex, it returns something. Oftentimes when you lock it, like back in C++, when you used to lock a mutex, right? You don't return anything, right? It just like, it has some side effect, right? But here, locking returns a reference to what's inside, right? It returns a reference to this longest article, and then now I know I have exclusive access to that longest article, this shared piece of global data, or I guess global in terms of that all the threads can see it, right, and update it. And now I can perform this check. I can say if the length of the current article is greater than that of the longest article, I need to update what is the longest article. And then finally, I go through all the requesters in this batch and I join. So the batching logic, it's sort of like I spawn, a batch of threads and then I join. And then I spawn another batch of threads and then I join. You might be wondering, why do I need to do that? Well, let's see what happens if I just make the batch size really big, right? So if I make it 100, right, hopefully it should be able to withstand this, right? Does anyone have any predictions about what's going to happen? Cargo, same thing. What do you think happens if I just make the batch size too big? If I have too many threads at once, what could happen? Yeah, so that's a really interesting point. I'd say definitely for like CPU bound things, that's especially the case, right? Because if you don't have many cores and you're doing something like maybe you saw in CS110 lab with the quicksort example, then the overhead of context switching is gonna, not let you win by multi-threading. But here, because we're IO bound, I'd say like oftentimes just like having more threads in general is better because you can overlap more waiting times. Um, but yeah, are there any other thoughts for what might happen if we have too many threads before we just? Yeah, I mean that's a good point. So oftentimes deadlock happens when you have like more than one resource, right? That's limited in some sense. But I guess here we only have this one mutex, right? Um, so let's see what happens here. So I run it and it's building, and all right, it's gonna be so fast now because we have more threads. And oh no, what happened, right? Let's take a look at some of these errors. So error, it panicked. So the threads panicked. The threads were really sad. Failed to look up address information. No Dane server provided or not known. So, but before that, it was saying something about there being too many open files, right? Too many open files, right? And it did this, it got there really quickly. So yeah, what does that tell people? Right, can I just like, make as many threads as I want, like make as many requests as I want? No, right? We need to throttle ourselves in some regard, I guess.
So this probably doesn't make sense to people who haven't seen networking before, but when you try to establish a network connection to a server, like when you try to telephone a server to try to download some information from it, it creates a file descriptor that is linked to that server, that you can talk to that server through the file descriptor. So if you try to create too many connections to a server at a time, or to servers in general, if you try to create too many network connections so that you're downloading a lot of things at the same time, you actually run out of file descriptors. And that's what happened here, is the system crashed because it tried to open more connections than the system could handle.
Exactly. Really strained our operating system. We asked too much of it, really. And really the issue here, like another thing you should think about though is like you also don't want to like overwhelm other servers with requests either. Like that's also not a very nice thing to do. So like there are different stages of like limiting that you want to consider for the sake of not, I guess DDoSing different resources that you have. But in terms of like, there's some problems with this batching thing, and I'm not going to focus too much on it because just for the sake of time, just so that we can talk about other things. But like the main issue is that it's not very flexible, it's not very dynamic, right? Another thing is you can easily reuse threads, right? We don't have to spawn and destroy threads. You should really be using a thread pool for something that looks like this, but you'll have plenty of fun implementing that in assignment 6 of CS 110. And if like once you finish that, you might even want to implement it in Rust. I think that would be a great exercise. It might even be easier. So let's think about, can we do better than batching, right? We needed it because we didn't want to overwhelm resources. More effective way that you might have seen in CS 110 lecture with regards to semaphores was that you can use semaphores as a way to limit sort of like a number of permission slips, right? So I need to ask for permission to be able to start downloading an article. And this is one way to throttle ourselves, right? Is everybody familiar with this usage of a semaphore? Are there any questions about this usage of a semaphore? Okay, I think Jerry might have talked about this last week. And you'll see this definitely in the CS 110 assignments in assignment 5. I think a good precursor to that is if you want, I'll post the link Explorer example on the website, and you can try to upgrade that using a semaphore or using what we're going to build later today in order to throttle the number of requests. And that's essentially the same idea that you'll be doing in assignment 5 for CS 110. So in order to implement something like a semaphore, we need to first understand what a condition variable is, and totally understand if people are not down with condition variables yet, because Jerry just talked about it in lecture. But let's quickly go over what it looks like in C++. So this is the implementation of semaphore that Jerry presented in lecture. And as you can see, so a condition variable, I guess just to give a quick overview, is very similar to sig suspend that you might have seen in multiprocessing. And the idea is that you acquire a lock of some sort, right? So in the case of sig suspend, you were blocking signals, right? So you're saying, I don't want to respond to any signals just yet, right? You acquire some sort of lock, and then you check a condition, right? You want a particular condition to become true. But in order for this condition to become true, you need to let go of that lock, because something else is going to update it, and you don't want to like lock on it forever, or else you'll just be deadlocked, right? So what you do is you obtain a lock, you check a condition, and while that condition is not true, you wait. And while you're waiting, You're not blocking. You're not consuming CPU resources. You essentially think of it as like you're marking your thread as blocked, right? You're getting moved onto the blocked queue, so you're not wasting time on the CPU. And then you might get notified, right? And once you get notified, so in the case of Signal, we're notifying all who are waiting on this condition variable. Once you get notified, you wake up, you reacquire the lock, and then you're able to safely make that check. And then you do what you need to do once you pass, like in this case, decrementing the value. And then once that lock guard goes out of scope, it will release the lock. So I just said a lot, and I totally expect there to be questions, because maybe even if you didn't see this in 110 lecture recently, it might have been a while since you saw condition variables. So please, somebody ask a question about condition variables. Right. Okay, so you're asking, why do we need to notify all? So yeah, so the thing is, if you notify all of the threads will wake up, but only one will win. Only one will obtain, the lock. That being said, I think there's a subtle race condition if you don't notify all. And I guess maybe we can like talk about it after lecture. I don't know if Ryan, if you have like a quick way of like explaining that, why we have to notify all here instead of just notifying one.
Yeah, so it has to do if you have multiple threads that are waiting on a semaphore when you go to signal. This race condition can't happen if there's only one thread ever waiting on the semaphore. But if you can have multiple threads waiting on the semaphore, there's a really subtle race condition that happens with thread scheduling. It's actually on the 110 lab for next week, I think. And so if you want to talk about it after class, we can spend more time on it. But it's not crucial to what we're talking about right here.
Yeah, I guess in general, sometimes I think in certain quarters, like when Phil and Chris taught 110 in the fall, they're like, always notify all, because notify one is like weird and buggy, and like there are these subtle race conditions, and that's just like what you should do in general. But yeah, we could talk about
in general.
In general, you can't go wrong with notify all. It might be slightly less performant because you might wake up more threads than you need to. But what are those threads going to do when they wake up? The first thing that they do is they reacquire the lock, and then they check the condition again to see if it has become true. And say that like you've incremented this count by 1, and then you notify all. Only one thread is going to be able to get that thing that you just put into the semaphore, that you've just incremented the semaphore with, because one of the threads is going to wake up, it's going to see that the value is 1, it's going to decrement it to 0, and then it's going to return from wait. If there are other threads that were also waiting, then they're going to wake up, they're going to acquire the mutex, they're going to look at the value, and they'll see that, oh, hey, the value is still 0. And so they'll release the lock and go back to sleep. So nothing is wrong there. It's true that you had some threads that woke up when maybe they didn't need to, but functionally everything is going to work. On the other hand, notify one may be slightly more efficient if you can only have one thread that like successfully gets out of wait. Then maybe it's good to only wake up that one thread to reduce scheduling burden. But if you screw up with notify one, you can easily create deadlock in a system. Because say that there are multiple threads that are waiting for some condition, and maybe there's only one of those threads that can actually proceed from that condition. That's not really the case here with the semaphore, but it might be true in other cases. If you signal the wrong thread, notify one doesn't allow you to select which thread wakes up. And if you select the wrong thread and it's not able to proceed from the condition, then the thread that you did want to wake up is still asleep, and then your system may end up deadlocking because it didn't wake up. And there's a similar race condition here with semaphore. Even though you're not really trying to select one thread, it could be that you select one thread. Here is the race condition. You notify a thread to wake up that is currently waiting. And then before it actually gets a chance to wake up, some other thread calls wait and decrements the semaphore to 0 successfully. It doesn't even have to go to sleep because you just incremented the semaphore. Then the thread that you signaled to wake up checks the semaphore and it's 0. That thread didn't actually get to wake up. and you can end up with deadlock. It's a really weird race condition. It's a lot easier if I like actually draw out the threads involved and their states, but we can talk about that afterwards if you'd like.
Yeah. Are there any other questions about, I guess, just like the basics of how a CV works? Or maybe is somebody wondering, why do we have to acquire the lock before calling wait? Like, that's, I think, a totally okay thing to wonder. Okay, so, now we're going to talk a little bit about condition variables in Rust. I'm going to talk about it at a very high level, and then we'll actually get very comfortable with it, hopefully, in a coding example. In general, it's idiomatic to associate a condition variable with a mutex by putting it in a pair together. So I know we haven't talked about pairs in Rust, but you want to think of it as like a tuple. Like if you're familiar with like a tuple in Python, it's literally just, you can also think of it as like a struct with two things inside of it, and you use .0 to access the first thing, and you use .1 to access the second thing. You can think of it a pair as syntactic sugar for a struct that just has, like two things in it. And you can access what's on the left and what's on the right. So oftentimes, because, condition, and this is another way to think about condition variables, like mutexes are associated with pieces of data, condition variables are associated with mutexes, okay? And that transitively makes it also associated with that piece of data that the mutex is protecting. Right, so you don't want to have one condition variable that's responsible for multiple mutexes. Like you don't want to think about like, oh, I'm like saving so many resources by just using one condition variable for everything. That's gonna be so confusing. It's gonna make the code really hard to read, and it's probably gonna cause deadlock in some like weird subtle way. So that's why we just want to associate these two things together by putting them in a pair. Does that make sense so far at like a high level? Okay. So continuing forward, you have to clone that pair before you move it into a thread. And if a pair contains two things that are clonable, then we can just clone the entire thing. And really, so like the pair, when I say pair, it's like the arc. We're cloning the arc, is one way to think of it there. So we're not cloning the mutex. We are cloning a reference to the mutex. We talked about this last lecture. We talked about how bad it would be if we were to clone mutexes, because a mutex is supposed to be a limited resource. Really, we're cloning a handle to a mutex. It's like there's one thing pointing to it, now there are two things pointing to it, and now we have common access to the same resource. And you pass in the return value of mutex.lock.unwrap to cv.wait or cv.waitWhile. So before we would just, in C++, if we go back a slide, you would pass in a locked mutex to the condition variable. Now our mutex is the result of locking a mutex is going to return a reference to a piece of data, but this is a very special reference that indicates that it was returned from a mutex. And the reason you need that is that when this reference goes out of scope, it needs to unlock the mutex. And so you can just pass that reference into cv.wait, so cv.wait can unlock it while it's waiting. I imagine that was probably like a little bit confusing. Are there any questions about that? About like the difference between that and C++? Exactly, yes. And this reference is a special reference that gets returned from a mutex. You can sort of think of it as a smart pointer, I guess, because when that reference goes out of scope, it needs to let go of the lock on the mutex. Exactly. And finally, or I guess hopefully we'll see today, or I don't know if you'll agree with me or not, but the mutex and convar interfaces in Rust let you write safer and more legible code. Like I was surprised by how short the implementation ended up being. So let's talk about something, completely, or not completely different, but you've seen semaphores, right? They're really great. They can let you mediate access to a limited resource through, passing out a limited number of permission slips. And they can also like synchronize, you can also use it as like a signaling mechanism to indicate that a piece of data is ready, right? So you saw this in producer and consumer. in CS 110 lecture, right? Where you had a circular buffer and you said, I want to read from this buffer, but I need to wait until something is ready for me to read in that buffer. And we're going to do an example today that's very similar to this producer-consumer model. But semaphores, they're not that powerful. They just let you increment and decrement. That's not super exciting. Let's do something a little bit more interesting, right? Let's make a sema plus plus, right? So instead of just sema signal, let's do a sema.send, right? So instead of just saying, I want you to increment a counter, let's say, I want to send you a message, right? I want to put something in a queue, in your queue of messages to read, right? And instead of sema.wait, let's do like a sema.receive. And I'll just return something that was in that queue of messages. I think this will make more sense if we actually saw it in a picture. So let's just look at this real quick. I don't know how to like annotate things, or can I even annotate? Let's see, does that work? Wait, what
You
the
have to use
heck?
your iPad.
I have to use, oh wait, on my computer though. Here, I'm just gonna escape. Oh my God. Zoom, no. Here. Wait, sorry. Let's just go back here. Okay, I'm just going to show you in my mouse, with my mouse, okay? So what's going on here is that, say you have like a main thread and you have this sema plus plus thing, and you can clone it so you can share it with all of your child threads, right? And all of these children threads, you can think of them, say they're like workers, right? And they're going to be trying to perform some computation, right? And the first thread was successful in doing that, so it sends some actual result to the main thread. So it does sem.send comp result, and the main thread is able to read that by doing sem.receive. But thread 2, something went wrong. Maybe there were too many open file descriptors. I don't know. Or sorry, no, that was not sem 2. Sem 3, something went wrong. There were too many open file descriptors, and there's an error. So something weird happened. Oh no. Maybe sem 2 like did everything that was assigned to it. So it'll send an I'm done message so the main thread can register that. And similarly with thread 4, there's another result, and thread 5 just finished here too. So you've got this interface where you can sort of send like these rich messages, and the main thread can read them by calling this receive function. And if there are no messages sent, or if the main thread has read all of its messages so far, it should block until it receives a new message. Does this make sense to everybody? Are there any questions about this? About this like general setup?
To explain how this is like similar to a semaphore is usually, so Armin mentioned that there are two ways that you can use semaphores, and one of them is for communication between two threads, and it's for synchronization of communication. The analogy I always teach semaphores with, it's like a bucket of balls. It's a bucket of stuff that you can put stuff in, except you can't actually put anything in a semaphore. It's used for communication when you pair it with some form of data storage, like a vector or a buffer or something. So one thread will put something in the buffer, and then they'll signal the semaphore to indicate that something has been put inside of it. And then the other thread will wait on the semaphore so that it waits until something has been added to the buffer, and then it will read from the buffer. So the sema plus plus is just combining the data storage and the semaphore into one thing.
Yeah, so I guess can someone say something about like why might you want something like this, or why might this just be better? Yeah, it's less confusing. It's sort of like it gives you everything kind of in one package, right? If you use this, you don't need to worry about a mutex to synchronize access to that queue of messages, right? You don't need to worry about like manually calling cv.wait. It kind of just waits until it receives something. So it sort of like obviates the need for other synchronization primitives, right? We don't need to touch shared memory, or really implicitly we are using shared memory here still. But we don't need to like think about it as much, right? We don't need to worry about it as much. I think last thing I want to mention before we actually implement this, is that similar to like locks and stuff like that, you need to clone before you move it into a thread, because we can't just move our one and only thing into the thread. We'd have lifetime issues then, or like the reason we have to move in the first place is because of those lifetime issues. So I think that'll make more sense once we see it in context. But before we actually implement this, are there any questions? Do they act like a queue? Yeah, yeah, exactly right. So if two threads send, they'll eventually, like, once the main thread receives, you can think of send as enqueue and receive as dequeue. But like the dequeue operation is blocking. Like I'm gonna wait until there's something to dequeue, because if you dequeue an empty queue, you're just gonna get an error, and that's gonna be sad, right? But if you just wait until there's something to receive, that's how that works. It's sort of like when you call wait on a semaphore. You don't want to wait, and you don't want to go into negative numbers. Now you need to wait until somebody increments it. Does that answer your question? For sure. Yeah, I think there's also, I guess, you mentioned condition variable in your question, and you're asking like maybe if is there some sort of like queuing that happens in condition variables. Definitely, like yes to that as well, right? You need to maintain a list of who's waiting for this condition variable. So that's how that would be implemented. Exactly. It's done by the operating system. The operating system manages all of that and also can specify policies for like.
Okay, cool.
For sure. So are there any other questions before we get started in implementing this? Okay. So I have the finished example here, but let's start with a mostly fresh example. So I'll explain what's here already. So before we actually implement it, let's look at how we'd use it, right? So let's look at what it would be like to be a client of this interface. So we define the Sema++. It's going to be generic, right? So we'll have, plenty of practice with generics, and we'll implement a trait for it, right? And it's going to contain strings. And you do Sema++ new to initialize a new. Oh, wait, sorry, you're still, thank you for that. There you go. Now you can see it, right? Lovely, great, okay, perfect. Let me see if I can actually close this bottom window. Okay, great. So you have this interface where you declare, so you have a particular number of threads. You create a clone of it. This is sort of what you do with a mutex as well, right? You create a clone of it, and then you move everything into the thread. The reason you have to move, if you don't remember from last week, is that you don't know if the thread is going to outlive this function. So you have a lifetime issue if you don't move it in. Because what if you end up having a reference to something in this function, and that reference just you end up having a dangling reference if that reference is no longer valid and you're still referring to it in your thread. Then we just do a semclone.send thread, I just finished. So this format bang thing, it's just like println, except it doesn't print to the console. It generates a string for you. Are there any questions about that? Are there any questions about how we use this thing? All right, so let's implement it. Let's start with sema send, actually, because that won't require any waiting. So what's the first thing I do? Well, actually, okay, before I even do that, let's look at what this sema++ thing is. You have a Q and CV, so you have this pair I was talking about, and it's an arc that's holding a pair. It's a pair, and remember, a pair is just a struct where you access the first thing by .0 and the second thing by .1. And what you do here is you have mutex. It's a mutex of a vec deque. So a deque is a double-ended queue, and it's just a queue implementation that we're going to be using. It's something that the Rust standard library provides to us. And then we have a cond var, a condition variable. And that's it there. And also we made this generic. So we can take in any type T, and we can put that type T into our vec deque. Are there any questions about that so far? About the definition? And then I think this is something that I didn't mention during the generics lecture, but people might be wondering, like, what's the difference between this T and that T, which is a totally fine thing to wonder. You can think of this as like, over here, we're introducing the name T. It's like sort of like a like a function declaration, like we're introducing the name T. Here, we're actually using it, right? Because over here, you could also like specify trait bounds. Like I could say something like, like clone plus, I don't know, like format like display ... but like we're not going to do that. But that's the difference between those two T's. Are there any questions about that in particular? I know that was like a common point of confusion that people had as they were working on the exercises. Okay. And then to construct a new semaphore, we just say arc new, and then we declare a pair using this syntax, and we declare a new mutex, and then we put in a vector or a vecdeq inside of it, and then we initialize a new condition variable. So that's how that works so far. So how should we start our implementation of send? What do you think we should do? So like at a high level, what do we want to do? We want to like, enqueue message, right? Like, but how do we do that? Okay, great. So how do I take the lock? Sure, right? So we actually have a pair right here, right? So I need to access the lock is the thing in position 0. So there are different styles for dealing with pairs, but just so we don't get bogged down in thinking about that, we can just do .0 for today. In the solution code, I show something that's like slightly more idiomatic, but yeah, but let's just do that for now. So we could say like let q equals, so what should I say? Self dot, what did we call it? Q and CV, right? Dot what? Dot 0, that's going to get me my mutex. Then what do I do? Dot lock, yep. And then dot unwrap. Yeah, we have to unwrap it. It's a very typical REST code, right? We need to, the lock's going to return some sort of result, and we need to unwrap our result to make sure that everything goes okay. Okay, great. So that's the queue. And now what do I want to do? Sorry, was there a question? Was someone saying something? Yeah, I mean, I suppose if your lock state was like corrupted for some weird reason, or if you tried to do a double lock, right? Sorry, what were you going to say, Ryan?
It happens when what we call the lock gets poisoned. So a lock gets poisoned when a thread is holding the lock and the thread panics. And the reason that that's considered a poisoned state is because you don't know what that thread did. It might have like partially modified some things, but not finished modifying everything. And so you should assume that the things that the thread touched, the things that the lock was protecting, are poisoned. It could be in an inconsistent state. We don't really know because the thread crashed in the middle of changing it. And so Rust allows you to not crash your whole entire program in case you actually want to handle that in some way, like maybe log an error message. And so that's why it returns you a result in case you still want to keep going. But you probably don't want to. You probably want to crash, and that's why we call unwrap.
Does that answer your question, Julio? Okay. Any other questions about what we've done here? I know this is kind of funky syntax. Like this dot 0 just gets the thing at index 0 in our pair. There's like other pattern matching syntax, but I don't want to like confuse people with that right now. You can look at the solution code in the slides if you're interested in what that would look like. So we have our queue. Great. What else do we need? So what do we do when we're sent? So now we actually acquired the lock, right? So what do we do now? So we have our queue. What do we want to do with this message? Like pretend this wasn't multi-threaded at all. What would we do? You want to enqueue it. You totally want to enqueue it. Great. So I can say q.enqueue, or not, dot push, it's actually called. q.push.
Push front?
Is it push? Oh, yes, push front. Thank you. We don't want to push it. Wait. We pop front.
Push back.
I don't think there's a pushback. Let's quickly look at vecdeq Rust.
By the way, double-ended Q is pronounced deck.
Oh, it's deck?
So
I've heard people say deek.
It's fun because it's called vecdeq.
Vecdeq. Oh, vecdeq. That's so cute. I love that. It rhymes. So there's a get with capacity, push. Oh, there is a pushback. Okay, great. Okay, perfect. Okay, I think I got confused because regular vector, it's just push. So that's why. Great. Okay, so it's push back. Great. So it's push back message. Okay. Great. Now what? Are we done? What's the last thing we need to do? So now we're going to remember that we're in a multi-threaded world. I told us to forget. Let's remember again. We're multi. Exactly. So how do I signal with this condition variable? First of all, how do I get this condition variable? Exactly. So I can do self.q and cv dot, it would be 1 in this case, and then what do I do? So like, what does signal look like for a condition variable? It'll have the same name that it had in C++. Exactly. We want to notify all. Notify underscore all. Exactly.
So in this case, isn't there only one thing waiting on it, which is the main thread?
Yeah, that's a good point. Yeah. So in this case, the way we have defined this abstraction, we'll only have one thing waiting on it if it's like a simple like single consumer thing. But let's say maybe we want this to be a little bit more general, and maybe there are multiple things that could wait for it, right? In the diagram I drew, though, you're totally right. That was just one thread. Yeah. Are there any questions about this? So I'm actually going to argue that we don't always want to notify all, or not. We don't always want to notify period. Is actually what I want to argue. Right? Exactly. Does that make sense? I think if in the semaphore example, you might have seen something similar, right? It's like only if value equals 1, you notify all, right? Because this is mainly just an efficiency thing, right? So how do I modify the code so I only enqueue, so that I only notify all once it became newly, say, full of something, or once it came from empty to not empty? All right, well, I can definitely wrap this in an if statement of some sort. Right, I think, let's see, I think it's called len. Let me just double check here. Len. Oh, self.len. Okay, yes. Great, okay, yeah, so you can just call len just like a regular vector. So if I say if q, so kind of like this mirrors the semaphore example really nicely. If q.len equals 1, then we're going to notify all. Does that make sense to everybody? Any questions about what I've highlighted here? All right, so let's take a look at receive. That's exactly right. Yes. So yeah, you might be wondering, oh no, we locked something and we didn't unlock. You never have to explicitly unlock, right? This is an example of RAII. The fact that that once this thing goes out of scope, oh, I highlighted all of it. Once this thing goes out of scope, right, it's going to automatically unlock, because this lock.unwrap is not just going to return the entire queue, it's going to return a special reference. So actually, let's look at Rust's mutex Rust. Let's look at that together. If you go, let's see. Let's look at the return value of lock. Oh, it's right here. Okay, great. Return value of lock is a mutex guard. It's a lock result. That's why we have to unwrap it, but it returns a mutex guard. What the heck is a mutex guard, right? An RAII implementation of a scoped lock of a mutex. When this data structure is dropped, the lock will be unlocked. The data protected by the mutex can be accessed through this guard via its deref and deref mute implementations. Okay, so that's very advanced. We haven't talked about deref and deref mute, but I think they're very fascinating topics. These are two traits that let you, this is how smart pointers work, really, right? So like you might be wondering, how is it that I have like a box containing something or an arc containing something and I can just do the dot operator on it, right? It's because these traits let the dereference, they overload like that star operator. They overload the dereference operator and let those references sort of like pass through to the inside data. So this mutex guard is just like another smart pointer, except, so like that's why I'm allowed to do things like, if we switch back here, that's why I'm allowed to do things like q.pushback. So this q is really a mutex guard, but when I do dot pushback, this pushback doesn't happen on the mutex guard. It happens on what's on the inside of the mutex guard. You can think of the mutex guard as like a box, and it's like holding a piece of data, and this pushback goes straight through the box into that piece of data. But that's more of like an advanced point about how are these things actually implemented. But to your point, right? Like once this is dropped, it unlocks the mutex automatically for you. Are there any questions about that? I totally expect there to be, because we haven't talked about deref or deref mute. But if you have more questions about that, I'm happy to talk about that after lecture. Any other questions? Okay, so in the last 4 minutes, let's do receive. How's that supposed to work? So what's common to what we had before? What's the first thing I do when I want to wait on some condition variable? Exactly. So let's take the lock. We can literally do the same exact thing that we did before, and we'll indent it back. So we take the lock. That takes the lock. Now what do I do? Well, so the dot receive will receive, it's just going to do it one by one. If you want to get more than one message, you got to call it multiple times. That is how we're defining our abstraction to work.
Yeah, it may be confusing because we explained this in the context of like one use case, which was the main thread receiving a bunch of messages. But here we're just really trying to define a general abstraction, sort of like a semaphore can be used for anything.
Right, so here notice we're calling sem.receive in a loop. And we're doing it for the number of threads. So now so I know I haven't really showed you the syntax for cv.wait, but it looks something like this. So I do self q, I can't spell q, and cv.1, and I'm going to do something. Okay, so I'm going to do this thing called wait while instead of just wait, so I don't have to call it in a loop. So it's going to be wait while. And wait while takes two arguments. The first one is the lock, so it's going to be this q thing. And the second one is a function, or a closure, right? So I'm going to define this, and this closure, what it's going to do is it takes in this thing, right? It takes in this q. And what I can say is something like this, right? I can say, so what is the condition I should put here? Can somebody tell me? What do I want to wait while what? Exactly. And another way to say that is while the queue is empty, right? So while q dot is empty. Exactly. So then that's gonna let me wait while that's true. Now what do I want to do after I've waited? Exactly. And the way we do that is we do this thing called pop front. Pop front actually returns an option, but I know that this is not going to be none because I waited until it was not empty. So I'm just going to go ahead and unwrap that. Final thing here is we need to implement clone, but you'll notice that there's only one thing in this struct, and it's an arc. An arc implements clone for everything. So I can actually just get rid of this. Like, we don't need to do it manually. What should I do instead? People remember what this is called? Derive, exactly, derive. Just like calculus, we derive, we do derive clone right here. That's all we want, right? And that derive knows that it can clone because the only field in this is clonable. It's an arc, right? So that looks good so far. In the last minute, let's see if this compiles. Cannot borrow Q as mutable. Ah, okay, a classic Rust error. Let mute Q. Let mute Q. Great, okay. Great, and let's see what this does. Unnecessary parentheses around if. Ah, okay, so borrow of moved value Q. Move occurs because it has this type. Okay, so it's moved inside there. Okay, so how do we get around this? So this is kind of a weird issue right here, right? Okay, yeah, let's try that. What if we just gave it a reference to the Q? Oh, mismatched types. Expected a struct mutex card. Oh no. Wait, 1 second. Ah, okay. Right, okay. Okay, so this is actually what's going on. The cv.wait will return this lock handle to us. So really what I want to do, this is a very subtle thing, but what I want to do is something like this. So I want to lock it here. Right, okay, sorry, that's an egregious line of code. There's a lot going on there. Right, so I want to lock it there. And then, let's see, yeah, what's the proper way to indent something like this? And then I want to say let mute Q equals the result of wait while. Because wait while, I forgot to mention this, wait while has the same return type as mutex. So I can say let mute Q equals self.q and cv.1.wait while. And because what happens is after the wait while finishes, it still needs to reacquire that lock. And if we recall, right, reacquiring a lock returns something, right? So it's going to return this particular thing to us right here. Because Q, well, so the capture, so this Q, this is different. This is scoped to whatever the return value is. So yeah, so what this returns, that's passed into the capture clause. Another thing is this just like .lock, this returns a result, so you need to unwrap it as well. So let's just see what that does. And oh, come on. Great, it worked. So that's, and just to show you, it can do different things every time. Oh wow, thread 5 finished first, right? You can just run this over and over and race the threads. It's really fun. But yeah, okay, so this was definitely, I kind of rushed through that at the end. So I'm happy to stick around and answer questions about what's going on here, especially in receive. I feel like we didn't have that much time to talk about what was going on there. Are there any questions about this? Or I guess what questions do people have about this?
Also, if you need to go,
feel free to go. Yeah,
coming in. We'll see you on Thursday.
Yeah. I imagine this wait while thing is not the most intuitive thing. Okay, so let's go back to what was going wrong. So actually, let's talk about what's happening now first, and then we'll go back to what we had before. Before we could have actually made it work, it's just we ended up losing our reference to the lock, right? So what this does is this moves the lock into the wait while, right? But that's okay because the wait while is going to return it back to us. So let's see if I can go back to what we had before. We had this before, right? Wait, there. Okay, right. So we had this before. Let's run that, and it got angry. Oh wait, no, because this is one of the classic Rust ways to fix compiler errors. Just add random ampersands, right? Borrow of moved value Q. Okay, that's definitely not good. But I argue one way we can, so the issue here is that, look at this, right? this moves Q into wait while, and then we try to use Q again. That's not okay. But if I said Q equals, let's see what happens. Oh, mismatched types. Found enum result. Because I did not unwrap. Okay, unwrap. It returns a result, just like dot lock. Okay, let's see what happens now. And that works. So actually, there's a very small edit distance from what we had to do. Does it make sense why the unwrap had to be there? I think Ryan explained this before with like the lock poisoning, right? Like why does something like dot lock need to return an unwrap? But I think the main point of confusion was why couldn't we just do this, right? So if I just commented this out, it's going to become angry with me again, for sure. Borrow of moved value. So if we look at the wait while implementation, CV rest, oh, that's not what I want. Rest condition variable is what I want. If we look at wait while is here. Oh, at the bottom. What does it take? It takes in a mutex guard. Notice how it takes in a whole mutex guard, not an ampersand mutex guard, not an ampersand mutex guard, but an actual bona fide mutex guard. It wants to consume the mutex guard. Does that make sense?
Okay.
Exactly, right? So it takes in this guard, but it gives it back to you. But the reason it needs to take it in is because it needs to, like, while it's waiting, it needs to, like, release it. It needs ownership of it, actually, right? But then after it's done waiting, it'll give it right back to you. This is actually a pretty common pattern you'll see, because sometimes we don't want to make sure, we don't want, like, multiple mutex guards, like, running around for the same reason that we don't want to clone them, right? But it's okay to just say, like, wait while it's like, I'm going to hold on to it for a little bit, okay? And then I'll give it right back to you in the return value, because if you look at the return value, it's the same exact guard that was passed into it. Does that make sense? Maybe it's better if we look at the code again, right? So the code, it was just consuming this queue, and we tried to use it. And that's why it was angry. But if I comment it back in, if I just say Q is equal to what it returns, then it's happy again.
So to give like a bird's eye summary of what's going on, cv.wait takes a locked lock. That's true in Rust, that's true in C++. You have to lock the lock first, and you pass it to cv.wait. It's nice here because the type system ensures that you actually have locked the lock, whereas in C++, a lot of times we see students who will pass a mutex to cv.wait, but they didn't lock the mutex first, and it actually ends up creating race conditions or worse, deadlock in some cases. So you have to pass it a locked lock, which is why we do this lock on the first line, and then we pass it in as a parameter to the second line. But you have to pass ownership, because if you don't pass ownership, then there are two references at the same time to the underlying data, and it's possible that you might end up modifying the data using one reference at the same time that it's being read using the other reference. So that's why it needs to take ownership of that lock guard, of that mutex guard, so that it can evaluate the condition,
reading that variable, and so that it can also unlock the lock when it goes to sleep. When it comes out of sleep, it has to lock the lock again. And remember, I mentioned this thing about lock poisoning. If a thread panicked while holding the lock, then when you try to acquire the lock, you'll get a result error out saying that a thread crashed while holding this mutex, and you can't trust that anything inside of the mutex is consistent, because it may have corrupted the data inside. And so that's why you need that unwrap, so that when it reacquires the lock, and if it's poisoned, then it will return you an error saying, hey, this data is poisoned. We probably shouldn't continue, but if you really want to, we can. We have to take ownership back, because otherwise we won't be able to use the data inside the lock again. We would have to to reacquire it, which you also could do, but a lot of times that creates another race condition. So this is the way that you typically will receive ownership back, and then we can use the queue normally.
I mean, I guess we can't even reacquire it if we wanted, because it's already acquired by the
You
return
can,
value.
because it will be dropped. It goes out of scope at that after that function. So if you're not receiving the return value of that function, then the value it returns, which is the lock, gets dropped.
Oh, I see what you're saying. I see. So you're saying something like if you just got rid of this, but then you just tried to lock it. Yeah.
Right.
Okay.
But if you did that, it would create this race condition where here you have waited to make sure that the queue is empty, and then if you're not still holding the lock, like if you momentarily drop the lock and then reacquire it, some other thread could get in there and steal the thing that you saw inside of the queue. So that when you do queue.pop front, actually now the queue is empty because some other thread got in there and stole what was inside. And so when you unwrap, you risk crashing.
Yeah, I think this is similar to the race condition that you were talking about with Trip, right?
Yeah. Where like we waited for the semaphore to become 1, but then if you release the lock and reacquire it, the thing might not be there anymore. It's a little different because in that case it was an issue with condition variable usage, not with mutex usage.
Right.
But this is about mutex usage.
Mm-hmm. Are there any other questions about just like this example as a whole? Let me see if I can minimize this. Oh, close. It's being covered. Right. So if we just look at it all, I mean, I think it's kind of remarkable how brief it is, right?
Very brief, but also complex.
Yeah, that's kind of like the trade-off with Rust. Like, so maybe a couple of lines of code, but you're like, what the heck is going on?
Well, I think that's true of C++ too. I think it's the fact that it's multi-threaded. And the difference here is that Rust prevents you from making a lot of the same mistakes that C++ and C let you make through its type system. Like, because it requires you to get to the data through the lock, like there's no other way to get the data other than by having the lock. Mm-hmm. It avoids most lock issues. And then similarly, because the CV requires you to pass a lock guard, a mutex guard, instead of a mutex, that also ensures that the mutex is already locked, which is a common mistake we see people make.
Yeah, and I think
it also prevents you. Another mistake some people make is they don't fully understand what CVs are and why CVs require you to pass a lock. And so they get the condition part, like they'll pass the condition correctly, and then they're like, oh, well, wait takes a mutex as the first argument.
I'll just make one.
So I'm just going to declare a mutex and pass it. And it's like, what? No, that has nothing to do with, like, you need to pass the mutex that is guarding the data inside of your condition. If your condition checks a variable, you need to pass the mutex that guards that variable. But because C and C++ make no association between locks and data, it's easy to make that mistake where you just pass a random lock, or worse, you think you're passing the right lock, but actually it isn't the right one. And Rust removes all of those issues by enforcing an association between a lock and the data that it protects.
Are there any other questions about that, or about like this example in general, or about like CVs? Yeah, I think that's like one good way to put it, right? And it's oftentimes like that the pieces of code, like you can sort of think of it as like these like little critical regions, right? Of like where you have the lock and unlock. Oftentimes they have to do with accessing data, right? Accessing data or modifying this, and you saw this in assignment 3 with blocking signals, right? You would block signals around, this check, like num workers available, or when you're like pulling things off the queue. So really like that act of locking was, even though like the code was a proxy for like protecting like pieces of data, which is, and I think it's like a bad proxy for it because it's really hard to reason about, because there's sometimes there are like really subtle ways, like maybe there's a decomposed function that touches that piece of data, but you didn't know that because it was decomposed, and maybe they didn't like properly lock around it, right? I guess, like, Ryan, do you have anything to say to that?
Yeah, I'd say that under the hood, it's really the same. So I don't know if have you seen lock guards in 110 yet? So this is mechanically the same as a lock guard.
But it doesn't protect a piece of data. A lock guard doesn't protect a piece of data.
Right, but the way that, like, if you think about this in terms of an imperative program that like does one thing and then another thing and then another thing and another thing, it's the same. You lock a lock and eventually you unlock the lock. In C++, if you're using lock guards, the lock gets locked when you create the lock guard, and it's released in the lock guard's destructor. That is basically the same thing as what's happening here. When you do something .lock.unwrap, that is returning you a mutex guard. It's really a lock guard. And then in that object's destructor, in the drop trait, when it goes out of scope, the lock gets unlocked. The difference is that the data is declared inside of the mutex in Rust.
Whereas in C++ and in C, a mutex is a standalone object that just has like some state, locked or unlocked. And it doesn't actually contain the values that you're trying to protect. And then somewhere else, you declare the values that you're trying to protect. And it's up to you as a programmer to make sure that if you have some values that are accessed concurrently, you make sure that you don't access them concurrently by using a mutex so that you get mutual exclusion, and so that those would-be concurrent accesses, would-be dangerous concurrent accesses, are serialized. But that means that you have to document in comments, you have to say, before touching this variable, make sure that you're holding this lock, because otherwise, some of your code will acquire the lock before accessing the variable and release it afterwards, and that is safe. But if you have some other code somewhere else that doesn't respect the lock and goes straight to the data, doesn't matter about all of the work that you did on the safe code, that those couple of unsafe accesses will destroy everything and create race conditions that could potentially crash your system. So you have to make sure that everywhere you touch that data, you acquire the lock and release the lock properly, which is pretty difficult to do. And especially for large code bases where you're bringing on new developers regularly, you have to make sure that these new developers respect your practices of acquiring the lock before touching the data and whatnot. And if you have comments saying, hey, acquire this lock before touching this data, you have to make sure your comments are up to date, which is often not the case. And I got bit by this a month ago in the Linux code base because it said, acquire this lock for these fields. And so I'm like, okay, I'll acquire those lock for those fields. And then I touched some other field, which wasn't in that list. And it turns out you actually needed the lock for that field too. And so this Rust approach of saying, you can't get to the data unless you acquire the lock. Like, you can't mess up here. You have to hold the lock in order to have access to the data. That approach is nice because it makes it so that you can't have these accidental mistakes. You can't have new developers that don't realize that they need to hold a lock. You can't have stale comments. It's in the code itself. Like, there's no way to touch that data without holding the lock. That, I think, is the difference. Mechanics are the same, but it's the compiler's type system and this like monitor design that Armin was talking about that forces you to make sure that you're using the lock correctly.